Well, good morning. I'm here this morning to do a discussion about the feasibility of this plan that I have in front of me. So often what we find is that we develop plans and I'm speaking for myself and for many other people here, that we develop plans and then don't necessarily assess the feasibility of them completely, or just do really basic feasibility studies. And that's something that we, on this particular plan, we sought to take up to another level. We've certainly done a number of feasibility studies over the years, but with this one, we just wanted to take a bit of a deeper step, and in doing so, really get an analysis between the amount of, to summarise, to get the amount of extra forage that this Keyline irrigation system would generate. So here's the property as it stands right now. Oops, I'll just change the resolution. Take off that Vic map. So here's the property as it stands right now. These green areas that are marked are what we've classed as the arable zones, and there's about 174 hectares of that out of the full 1,000 hectares that are available. There may well be a bit more than that. We've got to do a bit more land analysis, but that was a starting point. From that, we then sought to create a design that would allow us to irrigate much of that. So let's have a look at what we did there. And we started off with a concept plan where we built those. We built all of the dams on the site and a series of irrigation ponds, series of irrigation dams, and then irrigation systems. I'll just click off that arable area for a moment. So this is what we've got, and there's actually quite a few very, very efficient dam sites on the project site. And so what we found was 15 different dams, including a couple of turkey nest systems, which I'll describe in a moment, and actually 3 different turkey nests or crest dams, and then we've got flood irrigation systems. So this is a very conventional keyline layout from that perspective. You'll notice there's black lines here. The black lines is the proposed grid of probably 2-inch or 50mm polyethylene pipe. You'll notice that it follows the ridge lines predominantly, which is except with a few exceptions, but it follows the ridge line mostly, and that's follows the sort of signature of our approach of our systems. You'll notice also that in the case of this one here, where we're going down a ridge and then up a valley to equalise the pressure, and this is not to take out the need for air release valves, but we've also added in a loop. So this is a closed system from this point down. So where possible, we try and do that as a scheme as well. But now that system there would be driven by the gravity of which would be driven by some large tanks in this zone just here, and then this turkey nest system, which is on one of the higher peaks. This is the highest part of the property right here, well, the highest part that's closest to the pipeline. There's a couple of higher peaks over here, and then obviously you can get up into here and it's higher, but back up into here is probably the highest point on the property, but it's well away from the main agricultural zone. So, and the distances are quite reasonable on this place. So, if you look at from here to here, we're talking about 4 kilometres. So, pipe distances and the feasibility of pipe start to really play into planning and feasibility. So with that, there's this large dam that's proposed right here. It's actually quite an efficient site. really it has naturally available to it a small area of irrigation. It's only about two or 3 hectares, and from that we're looking to pump up to this dam here. That pipe is only 500 metres, so of 63 millimetre pipe in this case, and we pump up to that, and then that provides the head of pressure, which would be sufficient to not only do stock water but also to do Keyline irrigation, which is another kind of irrigation system using movable sprinkler heads that are towable behind a quad bike. So it has more moving parts, and it's more water efficient. But the big problem with Keyline is that it needs 30 metres of pressure, so 3 bar of pressure. So we have to either use a pump, or we have to be 30 metres below this point here before the natural gravity takes over, and that's not. We've also got to include in the calculations of that the friction loss that comes with pipe distance. So that's the nuts and bolts of it. Some of the systems that really excited us, are this system here and this system here. This system here, we've got 20 hectares that we're able to irrigate at about 1.5, nearly 2 megalitres per hectare, which is not a high rate of irrigation, but certainly one that warrants attention. Here we have another one, which is dam. That's got that. This dam here, dam 9. It's able to irrigate. These two systems here are basically able to irrigate this whole area, which is about 30 odd hectares. So we've got the potential, looking at these systems, with the capital that's applied, to irrigate quite a substantial amount of area. These systems here, again, you can see another 10 hectares here, 6.5 hectares here, and then some smaller 5s and 4s and so on. These systems here are also looking to be quite worthwhile. So let's have a look at the spreadsheet that we've developed in conjunction with this. Oops, let's get out of that. I'll just make this full size. It's quite a big spreadsheet, and so it fits on the whole screen that I've got, at least. So what we've got here is, let's get my pen going. What we've got here is, I'll just erase. Okay. I'll just go through it here. So to start with, over here you've got the dam project estimates. So with that you've got the name of the dam, and down here there's a range of different scenarios for each dam, so or pond as some parts of the world call it. And so when you look at it, we've got dam 1 to 15. Some of these dams are turkey nest, which is why we've got TN. The rest of them are barrier dams. So these are all what would be classed as key point, valley, or barrier dams. They're dams that are all within a valley. The only exception is the other turkey nests. You'll see that there's multiple options for each. The reason for that is because we wanted to look at the relative efficiency of the different storages, depending on the wall height and wall position. So there's a bit of work there. So wall height is listed here. Then there's the wall volume of the different scenarios. Our friend and colleague, Georgy Pavlov in Bulgaria and Poland, he worked on developing the 3D renderings or grade drawings in CAD of each of these using Civil CAD. And so I did the concept planning, flicked that over to him, and then he was able to do the 3D models for each, and in doing so, create the content that we were able to fill in here. So you can see here the embankment volume is relatively equal to the pit volume. So that's the pit is the cut volume. So we've tried to get that as close as possible. But the real game is to try and make those two as close as possible so that you have a very efficient earthworks process, but to get the highest amount of water volume for that, and with that as well is what's called the storage ratio. And the storage ratio is the ratio of water volume that is stored versus wall volume or cut volume that's needed to get there. So this storage here, dam number 1, which we can look at, is back here. Dam number 1 is this one. It's a really efficient dam. If you come in closer, you can. Whoops, I'm going to get back my pointer. As you can see, it's quite a nice dam here. It's got. I'll click on Georgie's drawing, so you've got that. There's the embankment that Georgie drew. Really small amount of earthworks. The embankment volume in this case is quite small, and the amount of water that's impounded as a result is really great. And when we looked at this site on site and using the flying camera that we had on site, it looked immediately we were sort of drawn to it. It's a natural key point of the valley. You can see we've got two quite flat runnels that come to this point, and we selected it because there were 2 ridges that came quite close together, and then there was another little runnel that came down here. So plenty of catchment. That being the case, we still put a catchment canal here, and one that was here, so a channel that caught all of that water. This here is the catchment area of that particular dam. So so it's a good one. This channel here, just as an aside, I put in secondarily, and it harvests any water that comes from these dams here and irrigates this whole zone. Anything that's left over would then be collected and come back into this storage as well. So there's some good aspects about that particular siting, and then it's a very cheap dam to be able to irrigate a pretty decent amount of terrain. So I'll go back to the spreadsheet, and the next part about this, I'll just change the pen colour to orange, not pink. The next part about this is the depth. So the depth of the storage is important, but not important in the sense that, important because we want to have a minimum of about 4 metres with this evaporation rate that we get in this part of the world, which is around about 1.5 metres a year. The area gets anywhere between 500 and 1,000 millimetres of rainfall, so 20 inches to 40 inches of rainfall a year, mostly winter. But it does get some summer storms, which currently are ineffective, but with this Keyline system and what we're doing in terms of landscape management with holistic planned grazing, that will surely change. So, but you probably get about anywhere between 10 to 30% of rainfall comes over the summer months. The rest of it's autumn, spring, winter, so the cooler months. We also had, as a function of that, is also the wall height. So wall height, while we've got 5s all the way through here, is, with a few exceptions, is that we had a look at the regulations, and that's a starting point in any process. And we have regulations and regulatory compliance in the climate section or climate layer of the Agrarians platform. Is that we found that a 5 metre wall height was the maximum height before it triggered a full engineered design. So, and we're not afraid of getting engineered designs done, but the cost that applies to a project is not inconsiderable. Plus a whole permitting process that also lengthens out the timing between when one can applies or goes through this kind of phase and then when it actually gets built. All the time, costs are rising. So for that, we've kind of looked at, all right, well, what would be a really optimal site? From when we looked at the site, we said, all right, if money weren't an object, and we just saw the most optimal site for a dam, 2 ridges coming together, maximum apparent amount of water could be able to be collected. Well, let's look at that site, and so that's reflected in systems such as here, where we've got 15 metres and 14 and 18 and so on. Those bigger walls are all a reflection of sites that have those attributes. But even so, we've still gone along and positioned dams in what we see as being more efficient places, and then tested it. How much water volume do we generate by that? But also, what's the cost per megalitre? You've got a total cost, but then what's the cost per megalitre, and what's the relative efficiency from the perspective of a storage ratio? I'll just turn off notifications. Don't know how to. Anyway, maybe down here. Okay. So, no. Do not disturb. Thank you. Go away. Sorry about this. No fun, is it? Force quit. System preferences. See you later. Okay. So now we'll look at the other aspects of it, and I'll come back to some of those starting points in a moment. Water conservation estimates. So that's Water Conservation Channel, WCC estimates. So we give everything a code, just like we give dams a code. Everything has a code. Everything has a length, and then everything has a cost per metre. You'll see that when you use this, sorry, I didn't point this out before, so I'll just get rid of the drawings here, that what we have here, we have codes for everything here. So you just click on there, and it tells you if there's a formula involved in this column, then, or in this row, then it'll tell you what it is. Otherwise, it just gives you some sort of understanding about what each column is about. So, what we look here is that's the catchment area. I haven't completed all of these yet. That's one task I've got for these few here. Why these are important? That was another legislative trigger. If a catchment is over 60 hectares in this particular water locality, then that's a trigger for a permit process. So you could see here, this one here is going to have that trigger because the catchment area is over 60 hectares. And then what we have here is what the overflow would be. I've got two different sort of standard effects there where we're looking at from KD Nelson's dams and design and construction of small earth dams. Is sort of a classic on that score. We've got this data that's been applied. So amount of hectares, so catchment area, cubic metres per second of flow, that equals an inlet width on a spillway of needing to be X. So if it's nearly 70 hectares, then the spillway width in this part of Australia, with the kind of rainfall it gets, has a spillway width of 13 metres on the inlet. Ken Yeomans in Water for Every Farm, in the Yellow Book, Yeoman's Keyline plan, he had a basic parameter for determining spillway widths, and it's interesting how different that is. It's the square root of the catchment area, so it's considerably lower. So you can certainly go through a longer process to determine what spillway width would be, and we would do that, but as a starting point we've just used these ambit selections, such as what Mr. Nelson has suggested, so going on the higher side of things. In any case, so the next step is to look at the irrigation zone, or IZ. So the irrigation channel, or IC. These are the systems that we've got there. It looks like I've got a couple, made a mistake there. It should be IC1 and IC16. They're all of the channels that are coming out of the base of the base of the embankment in the sort of old Keyline style of flood irrigation, coming out of a lock pipe. So we've got a lock pipe which goes to the base of the embankment. So here's your dam, and here's your water level. At the base of the dam is a pipe with a valve, and that pipe, you open that gate valve and that runs out a channel which is blocked along the way periodically in sequence, and that flood irrigates there, and then you undo that block and then you go to here and do the next one, and so on. It just continues on. It's a very fast, it's perhaps the fastest way of using dam water to irrigate. It uses a lot of water though, but it's very efficient and pretty solid state. And these systems that have been developed are still in operation some 60 years after they've been developed, so with very little maintenance. So it's a very efficient system when you look at it that way, but not from a water use perspective, not as efficient as, say, something like Keyline, which we're combining in with this system ultimately. That said, I haven't brought in the Keyline estimates into this particular thing. That's another step in the pathway for me. So what we have here is, again, the length of each channel, the cost per kilometre to develop that channel, what irrigation zone it relates to, what's the area of that zone, how many megalitres per hectare, so that we'd be able to apply to each of those zones, and then per dam, and that relates to per dam. So this dam here, dam 1A, based on the quantity of water it has, where if we were to use it, then we'd be able to get 1.7 megalitres per hectare of water, which is okay, but not fantastic. We've put a target down here. So a target, which is low, is 2 megalitres per hectare. So that's how we've been able to calculate this figure here. So that figure there, if you look at it, is 20 hectares times the 2 here. It's very simple. So this here is where we're looking at a megalitre balance, and the megalitre balance is, are we above or below that? So clearly if we've got, if we're at 1.7, then we're below that 2. So that just shows us whether we're above or below that. And that all helps us in the decision making, which is what we're looking at here. What are the main parameters for making a decision about which dam we would actually go with? And I'll continue on with that as we go along. So that dam there is under in terms of capacity. If we spent another $10,000 or $11,000, the cost per megalitre actually goes down just by putting another metre of embankment height. The actual storage ratio goes up. And of course the volume of water goes up. So that's actually a pretty good story, that dam, where we can spend not that much more money in the scheme of the project, and the amount of the channeling and all of those costs stay the same. The only thing that not that they're big costs anyway, but we spend that extra 11. It costs less per megalitre. In fact, it's one of the 2 cheapest storages that we've got. And we get an extra, nearly 1.5 megalitres extra of water. So we have a much better situation there. That will grow a fine quantity of forage. So the scheme cost goes up in total per hectare. That per hectare when we're looking at the capital estimates. So the capital estimates are where we're looking at the asking this question: would we be better to buy more land? And if so, what's the cost of this land? So the cost of this land was $3,000 a hectare. So would we be better to build this storage and this scheme, or would we be better buying more land? So, because you've got to have all of these questions on the table. So that's what we looked at. So, but that's as a one-off. So just treat it as a one-off. These figures are kind of rubbery in the way that they amortize over time, which is another part of the way of looking at all of this feasibility. So when we look at it, we've got the scheme cost, and that's the total cost of the scheme, and that's, so if you look at it, that is the cost of the dam plus the cost of the water conservation channels plus the cost of the irrigation. Not piping, I haven't added that work in yet, but that's an additional. But the cost of all of the irrigation channel altogether, that's divided by the amount of hectares that is being irrigated. So that gives us a cost per hectare. This capital target is the relationship between that price, so the capital cost of the land, minus the cost per hectare. So clearly it's up on the deal, these ones here. This next one here is well down on the deal. Anyway, we'll look at that one in a while. Forage estimates. We've looked at the current forage yields, and we've just made some ambit work on there. Last year there was quite a lot of hay cut, so that gave us a fairly good indication of what was able to be harvested off the arable areas. It was a very good year though, one of the wettest, 10 wettest springs on record since the 1850s, so a very good year. In terms of the average across the whole holding, though, I've pegged that at about 3 tonnes of dry matter per hectare, which then, if we look at it from, I think it was, I think I worked it out at 15 kilograms per head per day. Don't quote me on that because can't remember, but I think I had 15 kilograms of dry matter per head per day for a standard animal unit, or a 450 kilo dry cow. That every tonne of forage would generate 66 animal days, which would then have a value, which is where this is coming from. The local market rate is $4 a kilo at the Bairnsdale market, which is the closest, biggest cattle sale market. And the records that have already been kept are showing that we're getting on average 1.2 kilograms of live weight gain a day. So that's how we're able to come up with that figure. So turning forage into dollars. So if we've got 3 tonnes per hectare, then that's 198 animal days per hectare or animal days per hectare. That equals $950 per hectare. Right, and so as forage goes up, then so does the amount of beef that's actually able to be grown. So again, we could go, this is a pretty broad brush over some details which are yet to be delved into, but it does give us a very good starting point for the conversation, which might lead into those details being delved into. So a very, I won't say a quick broad brush, but it's certainly a good start, and then it helps us to then say, all right, well, let's look at this all a bit more closely. And that means, looking at the, doing forage testing or doing more detailed forage assessments, etc., so that you can really get that honed in and so on. As well as adding engineering, adding engineering costs, adding the cost of lock pipes, adding the costs of gate valves and those sorts of things. So I would expect that some of these costs will end up being more. That said, we've also put an excavation cost at $4 a cubic metre. If I were to tender this job and say, well, look, I've got $500,000 worth of earthworks to do, then and I was to put that out to bid, to tender, then it's quite likely I'll be able to get a better price than that. So there'll be some ebbs and flows in some of these figures when you get down to it. So we're just starting with the general to start with, to continue the conversation, and as a template for others to play with. And of course, once we build more into this, then we'll build it. It will be built into this live Google Sheets template. So current forage estimates, as I showed, so they're that's the current forage yield in tonnes for each of the irrigation zones. So IZ1 in this case, it's 20 hectares. It's calculated that area by the current forage yield, so that 3 tonnes per hectare. So that's what that equals. The scheme forage is where we're looking at 20 times the expectation. So I've made an anticipated amount of increase of forage based on the volume of irrigation per hectare being able to be applied. So I'm estimating that with 1.7 megalitres per hectare of irrigation just on the natural pasture, then we should be able to get 6 tonnes per hectare of reliable forage yield out of that. It may be higher, it may be much higher. So, but that's just where we're as a starting point. So we basically double the forage yield, as is obvious, and so that gives us 60 tonnes of forage extra off that area in the forage balance. So then we look at the cost per tonne. So what we're looking at here is the cost of the scheme's forage. So that's calculated by us looking at the total amount of forage that's able to be grown divided by the total scheme cost. So that if we were to look at buying hay, then how much, because that's again, if there's a regional price for hay, would you be better off just buying hay than investing in this system, or just continuing on, right? So there's those options that one's got to look at. I looked at it over a period because it's interesting to look at these things over, excuse me, to amortize things over a period. And so in this case, I've looked at a medium length period of being 20 years. So if I wanted to look at that more in a live fashion, I can just go down to here and say, I want to look at it over 10. So I can look at it over 10, and that immediately changes the figure on all of this, on this whole column, it increases it because the amortization period is shorter. Similarly, if I wanted to look at it, say I borrowed money for $5 for 5 years, then how much would it be then? So there's those sorts of things that one can play with to determine what the amortization period would be and how that would work in with the cost per tonne of forage over time. So as you can see there, the cost per tonne is quite low. Again, in deepening the analysis on these figures, I haven't calculated the operating costs of the system either. I think that we'd have a little bit of guesswork on that to start with, which as we do, we try and be fairly conservative on that. So there'd be those operating costs and any maintenance costs that would be need to be put in there. So that would add we'd add another column here in terms of operating costs, which would then influence these costs at the end here. And the next thing is where we're looking at the financial returns on the forage itself, and in this case we've used the holistic management metric of animal days per hectare. It would also be if this was if you had these figures as acres instead of hectares, it would be the same formula. So we work out the number of animal days that a hectare, so the number of animal units that a hectare can support. So in this case, what we've got is this is the current. So off that 20 hectares, we've got 20 times the animal days here, right? So that's the value of an animal day is is right here. So so with that, we then looked at the scheme balance. So the number of animal days calculated by the that's off that hectare, multiplied by the current forage that's available, multiplied by the cost or the value per tonne of that forage. Now, the next scheme that we're looking at is here, where we're looking at the value of the proposed scheme. So, and how much that changes is reflected in the value change here. So, have we gone up or below? And then finally, as a metric again, is, and this is related to the, so we're looking at the value that we've been able to attain. So that equals the total scheme cost divided by the value. That gives us the payoff time for each of these schemes. So because that's the profit, if you like, above which just normal operations would be. So in that doubling, because it's a straight up double, which relates back to the figure here of a doubling of forage equals a doubling of value equals, and it would take us just over a year to pay back the cost in this. If we go to the next one, and this is where just adding on that extra meter of, we spend $11,000 more money, but the payoff time is actually 3/4 of a year because of the just how much more forage is able to be grown. So that's really important to look at. So that kind of metric there is really helpful. Now, we looked at it from the lens that you can't look at just one metric as being the, and this became obvious when really trying to work out which were the best options. You can't just look at payoff period as being the only thing, because when you look at the different metrics, and that's why they've got different colours here. So we've got the number 1, number 2, number 3, just using traffic light colours, that some of these are up and down relative to each other in the different metrics. So, for example, this one here is all, it's clear that this one is a winner, so it's the green. The other one's not bad either. Don't get me wrong. It's a good system. It has a short payoff period. Forage costs are low. Capital, it's like almost buying another 3/4 of a hectare, so it's good from, and that's just as a one-off. That's not over time. In this case, that's like buying almost another. Well, every 2 years, you could say you buy another hectare and a half. So it's got a lot of value there. And then, and you could certainly apply a metric to that somehow, where you'd look at, all right, well, over 20 years, how much land is this worth, if you like, in buying another property? Because it's always easier to manage an existing property. Well, in most cases, I would say it's easier to not have more acres to manage, but just to manage what you've got better. If we look at the next dam, Dam 2, we're talking about some fairly big expenses here and differences in expense. So the turkey nest system, well, that's as it is. It is what it is. It's an efficient. It's a barely efficient structure. But that's not its purpose. So it's just to look at it on the site. It is this system here. So we've got a storage up here. So it looks like in cross section, it looks like from A through to B, it looks like here's the crest exaggerated, and we've got an embankment here, and then we've got an embankment here, and then we've got water here. So it's designed to have water come down from this storage, and we pump that water up. Only got to pump up. These are 5 metre contours, so we've got 1, 2, 3, 4, 5, 6, 7. So 35 metre lift to get up to here. And then this storage, then it's cheaper to build that than a tank, and I'll show you what I mean by in a moment when we get back to the figures. Let's get to that. When we look at the figures, it's in volume, it's 4 million litres of volume, and it's $9,000. The cheapest tank in Australia is the Pioneer tank. Let's get that pointer back. Is the Pioneer water tank. And these Pioneer tanks are, just get the images. That kind of tank is, the cheapest one is 62,000 gallons, or about 250,000 litres, 60,000 gallons or so. It's $12,000 to $15,000. So, you're talking about a dam that has a value of $12,000 for only 0.25 of a megalitre, versus this one, which is $9,000 for 4 megalitres. So, which is 20 times the size or something. So, yeah. that's why we look at a turkey nest. Yes, we're going to get a bit of evaporation. Yes, we'll get a bit of seepage. Even if I lined it, it would still be cheaper than building a tank there. So it's something, if you've got the soil type and a flat enough ridge or crest, and it's relatively proximate without the big lift, then it's certainly worth considering doing. And we have enough water. So so I look at this scheme, and I've got, and that's just going back to the map. That's this dam here. Now you can see here, we'll just see if I can get rid of that cross. That's where we had an overlay earlier. So in any case, can I get rid of it there? Yeah. Okay. So you can see here there's three walls. This one here is this wall is it won't show me. Oh yes, it will. So if you go into the associated Google Earth file, this one there's this embankment, this one, and this one. This one here is obviously the 18-metre wall height, and if you look at the pardon me, wrong dam. Go back, pardon me. That'll take me back to where we were. That's this. So there's the 15, the 5, and the 4. So this one here is the 4, this one here is the 5, and this one here is the 15. Now, if you look at each of them in terms of value, you can see here that this one here, it has a very high cost based on the amount of material it's got to be moved. You know, it's got 36,000 cubic meters of material to be moved. It would trigger a permit and all of that, but the cost per megalitre is actually quite low because the storage ratio is quite big. But so it's a really great dam, this one, and I would look at that quite closely, even though it has all of these additional costs, because that dam could become, in effect, a big driver for the whole property for a lot of reasons. So then you look at the 5 metre, and that's this one. The 5 metre, it has a pretty good value as well. The cost per megalitre goes up a little bit. It's got a pretty reasonable volume. 23 megalitres is not a small amount of water. It's about 17, 18 acre feet. It's below the trigger for needing oversight and permitting, and it's not and it's still got a pretty efficient. It's 2.5 times water volume to cut volume, so to excavation. So it's an efficient storage. Then we look at the fourth one, the third option, dam 2C, and this is where, again, it's just such a small dam. It's for the purposes of this property, it wouldn't even serve for our stock water. So we look at it. Yeah, it's not cheap. It's got a pretty average storage ratio. I mean, 100% is is basically the same amount of wall volume as water volume. So it's not that efficient. It's still not a bad cost per megalitre, but it's just doesn't fit. So it's one that we wouldn't look at, I would think. And then when we look at that in the spreadsheet, that's even made more clear. So if we look in here, you can see that even though that dam is very expensive, it is, and this is one that I'm a bit iffy on, we'll need to talk a bit further about, even though this dam is very expensive, you look at the amount of forage that it produces or potentially produce, and it's significant. But then when you look at the cost of that forage, because of the high capital cost, it loses there. So that, which is interesting. I would add to that, though, that one of the things that I'd look at with this system is that if I have, just so that we're looking at this equitably, if I put water in this dam because I've got so much, because the area that I've got here, it's only 2.6 hectares, so it's a tiny little irrigation zone. I never designed this for that purpose, but in the calculations, that's what we're considering. This dam, though, I would be proposing that it would do a lot of Keyline irrigation. So if I was to calculate the amount of area that it could Keyline, supply as a part of the Keyline system, then that would very likely make this 15-metre wall much, much more efficient and more lucrative. So by this not all including Keyline, this is just a Keyline estimate at this stage. So Keyline irrigation, by it limits some of the figures. So I do need to add that column in, but it should be fairly obvious to you in looking at this that if we were to add those columns, that wouldn't be hard to do, and then we'd be able to look at the feasibility of each of these dams from the perspective of both of the kinds of irrigation systems that we're looking at. So that would suggest, therefore, that if I added, and we can just add this in, if I had the irrigable area go to, let's say, 40 hectares. Let's see what that does to the figures. Okay, so what that does is it brings the payment, so the amount of water that's now available, I'm still in if I go to 40 hectares, I've got 2.5 megalitres per hectare, which is still enough. Looks really good there in terms, I've still got a good megalitre balance compared to the others. The others are shot by us doing that. The capital target, I'm still below, but that's again amortizable over time as well. It's not so bad. The forage volume that I create and the cost of that forage goes way down to what it was before. So if I do undo, so it was before, it was 68, and then if I go to 40, it goes down to 19. The other thing that happens is the period of payoff. That's that again, if we go to, it's not that bad when we look at it here. 6 years to pay off a system with that much water storage, and when we're talking about 100 megalitres of water here, you can do a lot with 100 megalitres of water. Consider in some parts of Australia it's $2,000 to buy a megalitre. So if you add that in as well, and that's just as an aside, that's something else that we may need to look at here because, or we will need to look at because we will need to buy the water rights. So that's an additional cost to what we've got here. But we don't know what that price is because we're just entering that market. But that's another price. So we've got to consider these things in the whole to help us determine. But that, if it was that there was that cost, then we'd want to be irrigating as much area as we could, in which case that brings us down to 1.8. If that were the case, it'd be pretty hard for me to not recommend that system versus the 23 megalitre, just because I've got so much extra water available. Even though, like you look here, that's a critical figure. Like we have to stretch that out a lot. So I'd have to make it 20 hectares in order to get that to even 1.2, which is just not viable, really. So yeah, so that's something to consider in the play. So the value of spreadsheets is that you can do a lot of scenario work. So that's a good illustration of how that works. And just in closing, what I looked at as well was looking at the greens and selecting the greens. So obviously I didn't select dam 2A in this scenario, but if I had of, then that would be that would bump that up, but that would also bump the capital cost right up. But we've got, out of this whole selection here, we've got 446 megalitres of total storage proposed. A couple of these are not for irrigation. I'll just show you those briefly. That is, oops, that's these two storages over here, which are for stock water as much as anything else. There's a good dam site there, and there's a turkey nest, again, as a replacement for a tank, because it's cheaper for us to look at that. $1,200 to put 1,000,000 litres up there. So 1,000,000 litre tank, I think that last time I priced one of those, it was probably close to $50,000. So yeah, it's a no-brainer putting a turkey nest up there. And they're already done on this property. There's a couple here and there. So so we'd look at that, and that dam there would actually fill by gravity from dam 2 as well. So this dam here it's an opportunistic site, but as you can see, it doesn't irrigate anything. So you probably wouldn't even do it, therefore. In which case, when we go back to here, and that's why I haven't have I included that? Yeah, I wouldn't even include it. So I'll take that out. So I'll take that out, and I'll take that out. So we'd be looking at 435, and in terms of, I'll take that out as terms of irrigation systems. So I've got 434 megalitres of water storage. The cost per hectare, or cost per megalitre, is $1,100, which is pretty good. Again, that'll have to be benchmarked and have added against we'll have to add the cost per megalitre for buying water, for a buying water license. But we also have the cost per hectare of irrigated area. Again, if I go and add in that total, the total area that I can irrigate by Keyline, let's say I'll do that. That's this figure here. So I'll just make that, I think I'll put 40 in here. So I'll put another 40, say. And just change that so that it includes, is it 48? Right, the cost per the value per hectare changes a lot. Goes down to about 3,900. Now, that's something to consider in the whole, because some of these, this is where this capital target figure really comes in, and that's why, again, I'd be looking at, all right, well, how much are we looking to amortise that over? And we've got a 3-year payoff period based on the value that generates, which is the value of extra animal days per hectare that we're generating, to give us the value per hectare and the ultimate payoff period. So when we look at that, it's probably a scheme that's really well worth investing in. To give you a little bit of insight, the client and I have looked at this pretty closely, and what we're now looking at doing is another option, which is which I think is a very sound one, which is to not borrow funds to do this, but it is to just shift over to doing the following. So what we're proposing to do is to establish this black network of pipes, which doesn't exist at the moment, that black network of pipes will then allow us, there might be a few others that are added, that will allow us to, using existing dams and existing pumps, and as we've got down here, we've got there's about a 20 megalitre dam here, and that pumps up to a header tank here. We'll be able to, from that point, set up the main water grid ahead of all of this Keyline system being built. And from that, then using the methods of management intensive grazing or holistic management planned grazing, we anticipate with a fencing layout that supports that and management that supports that, we'd be able to get at least a 50% increase in yield. That's very typical in a shift from set stocking as we have now to management or planned grazing, and that the income that's generated from that will then be able to be used to invest in the development of the Keyline scheme. So instead of borrowing money, which the client is willing to do, we've assessed that it would be much better for the project and the financial sustainability of the project to use the money that's generated from within the project to pay for the improvements, not borrowed capital or his own capital reserves. So use cash flow instead of capital to create capital. So that's where we're at. So it's a fairly exciting site. Certainly when I saw it for the first time, I was very excited, and we can have a quick look at it here. As we have some photos here, and you'll see what I mean. It's a really lovely part of the world, and it has a whole range of beautiful vistas. Here's where we took some of the drone shots. This is where Dam 2 would go, by the way, and so this is where the homestead envelope is up here, and where we're looking at lifting water from here up to the ridge here. So, sorry, this is Dam 1. This is where we had that those runnels coming in, and then there was that last one, and then an embankment here, and then being able to flood irrigate. And you can see all the bales that were out from this year's harvest. So it's got a lot of attributes, this site, which really excite us, and with that, we're very keen to get the first shift into management, into planned grazing going, and then we'd look at building the remainder of this landscape, including all of the trees in the landscape as well, so that, which is another layer of feasibility. Anyway, with that, I'll thank you very much for coming along, and look forward to talking about this project more and more over the future. Thank you. Take care and good morning.